Hi, my name is Brandon, and this is my report for Lab 5, Faraday's Law. The purpose of this experiment was to visualize the effects caused by Faraday's Law by dropping a magnetic dipole, in this case a bar magnet, through a metallic loop, in this case a tube of aluminum foil. We then wanted to compare the results for time taken for the magnet to drop through the roll from our experiment and from a model that we created on Python. The main physics principles in this experiment are the Biot-Savart law for dipoles, which allows us to calculate the magnetic field of a dipole at any point in space. Next is Faraday's law, which allows us to calculate the EMF created on a loop by a moving dipole in space. We also use the equation for the force caused by a dipole on a loop. Next, we also used Ohm's law, which allows us to calculate the current from the potential difference and the resistance. We also used Newton's second law to calculate a gravitational force, and Newton's third law to calculate a reciprocal force. Our experimental results are that the average time taken for the magnet to drop through the tube of aluminum foil is 3.2 seconds. The results we got from our model are that the time taken is 4.1 seconds. In this report, we will first cover the experiment, then we will take a look at the code and the model, and finally we will address some final questions. For our experiment, the first step was to take measurements. For our magnet, we found that the mass was equal to 79 grams, and from our previous lab, we found that the magnetic dipole moment was 7.7 amperes meters squared. It is worth noting that we used a different magnet than the one recommended due to availability. For the roll of aluminum foil, we found that the length was 35 centimeters, the inner radius was 1.5 centimeters, and the outer radius was 2.2 centimeters. The procedure for this experiment was to hold the roll of aluminum foil upright, then we hold the magnet just above the roll and drop the magnet down through the roll. We film this process and then time how long it takes for the magnet to make it through the roll. We repeat this process 5 times and find the average time taken for the magnet to drop through the roll. We found that the average time is 3.2 seconds. Here we can see the magnet dropping through the tube. Now let's take a look at our model. The assumptions we made for this model were that the tube of aluminum foil is composed of small metallic rings, as we can see here. We also assumed that the magnet moves perfectly in the y-axis. The way this code works is first we define some constants, measurements, and initial conditions. Then we calculate the current caused by the moving magnet using Faraday's law, which is represented by the yellow arrows on this ring. Next, we calculate the magnetic field at each ring due to the magnet using the Biot-Savart law for dipoles. The magnetic field is represented by the blue arrow. Then we calculate the magnetic force at each ring due to the magnet, and we know that this is the opposite of the force on the magnet due to the ring. These two forces of equal magnitude are represented by the red and yellow arrows. Then we sum the forces on the magnet due to each ring, calculate the gravitational force on the magnet, and add these two forces to calculate a net force. Then we can update the velocity and the position of this magnet using this net force. We repeat this process as the magnet moves down the tube, and we stop once the magnet leaves the bottom of the tube. Let's take a look at our code. We start by defining constants, measurements, and initial conditions. Then we create an object for our tube and another object for our bar magnet. We then define two functions. The first is to calculate the magnetic field from a dipole at any point in space. The second function allows us to calculate the time derivative of flux, which is equal to the EMF in a ring. Then we create a loop, which doesn't stop until the magnet has exited the bottom of the loop in our model. We calculate a gravitational force, and then we calculate the magnetic force on the magnet due to every ring in the tube. We then calculate the net force, update the velocity and position of the magnet, and finally, we print our results. Here we can see the magnet falling through the tube. The colors represent the direction of flow of the current. We also plot the velocity versus time. As we can expect, the magnet speeds up until it enters the tube. Then it slows down and reaches a steady velocity until it exits the tube, where it speeds up again. Here we can see our final result, which is that the time taken for the magnet to go through the loop is 4.094 seconds. This time is slightly higher than the one we found in our experiment, and this can be explained by the fact that the magnet in our model stays perfectly upright all the way through, whereas in real life, the magnet tilts slightly inside the tube as it drops down, therefore reducing the magnetic force. Now we can address some final questions. We know that the resistivity of the conductor is proportional to the resistance of the conductor. So if the resistivity were as close to zero as possible, the resistance would be as well. We know from Ohm's law that the current is inversely proportional to the resistance, so the current would be much greater. If the current is much greater, then the magnetic force would be much greater. Therefore, the magnet would fall much more slowly, practically infinitely slowly. If holes or slots were cut into the tube, then there would be essentially less loops in the roll of aluminum foil. Therefore, the overall magnetic force on the magnet would be smaller, and the magnet would fall faster. In conclusion, we accomplished the goals of visualizing the effects caused by Faraday's law by dropping a magnetic dipole through a metallic loop, as seen here. We also compared the results for time taken for our magnet to drop through the roll from our experiment and from a model on Python, which we can see here. Our experimental results were that the average time taken was 3.2 seconds, whereas the results from our model were that the time taken is 4.1 seconds.